So in this video lecture we'll be solving a numerical, and this is a design numerical of uniaxial bending. In the previous numerical, that was also a uniaxial bending one, but in that what we found was what was the capacity of the column to take axial load and bending moment. So in that numerical, the area of steel was already given, the dimensions were already given. What we had to find was how much that column can take moment about a single axis and how much axial load it can take. But in this numerical, what they have asked is what should be the dimensions and what would be the area of steel, because that is basically your design problem, right? So what they have given is a short rectangular column is subjected to a factored load of 1400 kilonewton and a factored moment of 90 kilonewton meter. About minor axis, that is YY, the column has effective length of 3500 mm, use M25 concrete and Fe415 steel. Okay, so the moment that is being applied to our column is about minor axis. Now what is minor and major axis? This is, let's say this is the cross section of our column. If it is a rectangular column, one side has to be greater than the other side. So this side is greater than the other side. So let's say this is D and this is B. So the bending, when it happens about this axis, okay, about this axis means that this cross section is going to bend like this. Bending is happening about this cross section. Okay, when I say this word about a particular axis, at that time what you can do is that you can put your thumb in this direction. Okay, let's say you put your thumb in this direction and then you curl your fingers. Okay, so the curling of your finger, that will give you the direction in which the moment is going to act. So if your fingers are curling like this, then this way would be the moment that is acting about that axis. So about whatever axis, when we say a moment is acting, you should always use your right hand thumb or left hand thumb, whatever, right? Okay, and this is called as major axis. Why it is major axis? Because your width is this and depth is greater. Okay, and if I have to take moment of inertia about this axis, it would be BD cube by 12, correct? But when I take moment of inertia about this YY axis, what should be the moment of inertia? It will be DB cube by 12. So this is always lesser than this one. This is called as IXX. This is called as IYY. This is major axis moment of inertia, this is minor axis moment of inertia. And what is given to us? That the moment, factored moment, is acting about minor axis. So it is acting about minor axis means the moment is like this, about this axis. I hope you understood this. So step 1 always is to determine the size of column. So till now we have understood what the question is. Let us start with the steps. So determining size of column, and as usual in all our previous problems, what we had done is, all our previous design problems of column, we had assumed a percentage of steel reinforcement. So again I will assume a percentage of steel, that is rho. Let us say that rho is 2%. So ASC is 2% of AG, correct? Then we need to find the factored load from the given load if it is not factored, and here it is saying that it is already a factored load and the self weight and everything is considered into that. So PU is directly given, it is a factored load. Then we can use this formula which is there in clause 39.3, and we can find what should be the gross area. So finding gross area AG, PU is equal to 0.4 FCK AC plus 0.67 FY ASC. The FCK is 25 and FY is 415. So I equate this PU to this equation and I put AC as AG minus this is ASC from this equation plus 0.67 Fy ASC. So I get Ag as 9113.9 mm square. Okay, now one thing that you have to do in this problem is that since along with the load, along with the axial load, a moment is also given. So we have to design our column for a moment, given moment. We have to increase this area because see, this area is for short axially loaded members. It is not for the members which are having bending. Okay, so this area will not be sufficient for those members having bending. So we increase this area by, you can increase it from 25 to 30%. So I increase it by 30%. Okay, so I will multiply this by 1.3. When I multiply by 1.3, I get 11848.1.87 square mm. Okay, so this is the gross area that I am getting. Now I will consider one side of the column. I will assume one side of the column to be 300 because it's not given in the question. So I am assuming it, and generally if it is not given, you should take at least 300 mm because I guess it's given in IS 13920 that the columns should be minimum 300 at least. So taking 300 mm would be a safer side. So I am assuming width to be 300, and then when I divide this gross area by 300, I will get depth. So depth D is this area divided by 300, which comes out to be 394.94. I will take it to be 450 mm because taking 400 would be like very much nearby. So let us approximate more. I will take it to be 450 mm. I have rounded it up on a much higher side. Okay, so we found our width and we found our depth. Okay. Step 2 is to determine the minimum eccentricity and to determine whether it is a short or long column. Now to determine if it is a short or long column, we need the slenderness ratio. So it is L effective upon the least lateral dimension. Already effective length is given, which is 3500. So 3500 divided by 300, because that is the least lateral dimension, right? It is equal to 11.667, which is less than 12. Therefore it is a short column. Now we need to determine the minimum eccentricity. Although it is given that the column is being subjected to only one moment, I mean it is subjected to a moment about only one axis, that is the minor axis, we have to determine this minimum eccentricity to check that whether it is lying within the minimum eccentricity or not, and whether both the axes are undergoing moment or not. So Ex minimum according to this clause is Lx upon 500 plus dx by 30. Correct? So Ex minimum means that this eccentricity is going to lie on this xx axis. It is going to lie somewhere on this xx axis. Okay. So I will put the unsupported length, which is again 3500 I will be using because the end conditions are not given here. So I will assume the end conditions to be hinged. So when end conditions are hinged, the effective length is equal to the unsupported length. So I will use 3500 upon 500 plus dx. Dx is the dimension in the direction of x-axis. This is xx. So along xx, 300 mm is the 300 mm is the dimension, correct? So 300 by 30, which is equal to 17. Now this 17 is less than 20, so minimum eccentricity about x-axis I should take as 20 mm. Okay. Now I need to check that whether this 20 mm is less than 0.05 times d or not, because if it is less than 0.05 times d, then I do not have to consider this minimum moment generated by this minimum eccentricity. Okay, but if this minimum eccentricity is greater than 0.05 d, then I need to consider the moment that is being generated by this minimum eccentricity. So let us check 0.05 d. So 0.05 times dx, that is the dimension along x, is equal to 15 mm. So what we can see here is that our minimum eccentricity is greater than 0.05 times d. In all the design problems till now, what we had solved about column, we never got our minimum eccentricity to be greater than the 0.05 times d, right? So this time if it is coming greater, that means that we have to consider this minimum eccentricity. So this will lie on the x-axis somewhere here, and what this actually means is that it means that we are assuming our axial load, this axial load of 1400 kilonewton, to not act at center but to act at this point, at this eccentricity. Okay, so if it is acting at this eccentricity, definitely it will create a moment that is 1400 multiplied by this perpendicular distance. So it is going to create a moment, and that moment will be created about minor axis, because see, if this is the load P, then P into Ex minimum is going to generate a moment like this. So this moment is about YY or about minor axis. So always remember that moment about YY is equal to PU multiplied by minimum eccentricity in X direction. So moment about minor axis is axial load multiplied by the eccentricity in major direction. So Ex minimum multiplied by Pu. Let us see what it comes. So 1400 multiplied by 20 by 1000, converting this to meters, it comes out to be 28 kilonewton meter. But already it is given that our column is subjected to a factored moment of 90 kilonewton meter in that same direction. So there is no need to even consider this 28 kilonewton meter, because we are already designing for 90 kilonewton meters, correct? So no need to consider this. If had this moment due to eccentricity been greater than this factored moment, then definitely we would have to consider it. Alright. So since this is less than 90, we will be designing for 90 kilonewton meter only. So this we checked the minimum eccentricity along x direction. Now we will have to check minimum eccentricity about along y direction. So Ey minimum is Ly upon 500 plus dy by 30. Ly is again unsupported length, so it is 3500 by 500 plus dy is the depth along this yy direction. So depth along yy direction is 450, so it's plus 450 by 30 is equal to 22, which is greater than 20. So Ey minimum is 22. Then we'll check that whether this is less than 0.05 d or greater than 0.05 d. So 0.05 times dy is equal to 22.5. So this Ey minimum is less than 0.05 times d. Therefore, we need not consider the moment generated by minimum eccentricity along y direction. So no moment consideration required about x-axis, because the moment that would have been generated by this eccentricity Ey minimum, that would have been about x-axis axis, correct? Because Ey minimum would lie somewhere here. So Pu multiplied by Ey minimum would give you moment about x-axis axis, but it is not to be considered because Ey minimum is less than 0.05 times d. Fine. Now when we are satisfied that this is a purely uniaxial bending condition, if there had been a moment along about x-axis also, then this case would have been of biaxial bending. But since there is no moment about x-axis, there is only moment about yy, this is a uniaxial bending condition. Step 3 is to determine load and moment ratios. Okay, now this is something new, and here we are going to use something called as interaction curves. These interaction curves are given in SP16. SP16 is the aid to IS 456-2000. Okay, so I'll take you to that SP16. So I hope you can see this chart. This is given in SP16, and the chart starts from chart number 27. That is what we require. It starts from chart number 27. Okay, and there are multiple charts that are given in this code. So what is the criteria to select the chart? That I will tell you now. First criteria is to see the Fy. What is the Fy that is given in our problem? And in this code it is given for all the yield strengths starting from 250. So Fy is 250. Second thing that you need to check here is this. d dash upon capital D ratio. So what is d dash? D dash is nothing but your effective cover divided by the length or depth in that direction. So d dash upon capital D, this ratio is required and this is required, sorry, and the yield strength is required. Okay, now I'll show you. This is for chart number 27. Chart number 28 is for again FY250, but this time d dash by capital D is 0.1. Then chart 29 is for again FY250, d dash by capital D is 0.15. Then 250 and d dash by capital D is 0.2. This is chart number 30. Then chart 31 comes. This is for FY415, and you can see how beautifully they have done. For FY250 the color is blank, or color is just black and white. When it comes to 415 the color becomes red. Okay, so it is easier for you visually to understand that which chart you are looking at. So for 415 this is the thing, and again it starts from d dash by capital D ratio of 0.05. Then again FY415 d dash by capital D 0.1, then d dash by capital D 0.15, then 0.2, and after this FY500. So FY500 is given in yellow color. So again it starts by d dash by capital D of 0.05, then 0.1, 0.15 and 0.2. Okay, so I hope you understood how to select a chart. What we have to do in that chart I will explain you later. Just see. Now again one more thing, there are multiple charts for this also. So what you can see in these charts is that you can see there is a diagram given, and what it is written is compression with bending for rectangular section and reinforcement distributed equally on two sides. So these charts are used for uniaxial bending only. Like you can see the reinforcement is only on the two sides. There is no reinforcement here. So if you plan on giving reinforcement on this side also, which is generally done for biaxial bending, that is when the bending is on both the direction, then these are not the charts that you need to take. For them different charts are given. I'll show you. Yeah, so it starts for these two reinforcement distributed equally on two sides. This ends on chart 37. Then from chart 38, it ends on chart 38, and then from chart 39 again it starts with FY250 d dash by capital D 0.05, but this time the reinforcement is on all four sides. So reinforcement distributed equally on four sides. So if you are planning to use this, which is for biaxial bending case, then you will have to use from chart 39. Again it is given for all the yield strength and for different ratios of d dash by capital D. Then for FE415 500. Okay, so this way it is given. Then again for circular sections also they have given, which I will not be solving circular sections because we do not have that much time as well. Alright, our case is of uniaxial bending, correct? So we will be using charts that are of this reinforcement. And what do we have? We have our reinforcement as of grade of 415 steel, correct? So 415 steel, red color charts we will be using. Secondly, we need to determine this d dash by capital D ratio. Third thing, now how to use this chart is, let me take a chart which is fairly visible properly, because all these charts are scanned by them, therefore it is not very clear. Although, okay, let us use this chart. So this graph is about two things. First is PU upon FCK BD. PU is your axial load which is coming, divided by FCK into B into D, capital D. Okay, next is MU upon FCK BD square. So these two things you will have to find, and then you will have to plot them, and what you will get is these are called as interaction curves. This black lines that you see, they are all called as interaction curves. Okay, and you can see there is a ratio given. It is very blur, but that ratio is rho by FCK. Rho is nothing but your percentage of steel reinforcement, that divided by FCK. That this ratio is what you will be getting from these charts. Okay, so percentage of steel reinforcement divided by FCK is equal to something that you will get when you plot this against this, and wherever it comes, like let's say this rho by FCK starting from 0 per 0, then it is 0.02, 0.04, 0.06, 0.08, 0.1, 0.12, like this. So let's say that the intersection of PU by FCK BD and MU by FCK BD square lies somewhere in between, then in between 0.06 and 0.08, then you will take rho by FCK to be 0.07. Fine. So you will understand this when we do in the numerical. Okay, now there is one more thing that I want to explain here. In this diagram, you can see that they have given axis of bending. Okay, this is called as axis of bending. That is, about that axis the bending is going to take place. In our numerical, which is the axis about which the bending is taking place? It is the YY axis, isn't it? Right? Now you see in this diagram, if this is the axis about which the bending is taking place, the dimension parallel to this axis is B and the dimension perpendicular to this axis is capital D. Okay, so for this, finding this ratio PU by FCK BD and MU by FCK BD square, we have to go according to these. Okay, so you cannot consider 300 to be B and 450 to be capital D. No, you have to go according to what is given in this diagram. So if this is the axis of bending, then the direction perpendicular to it will be called as capital D. So 300 is your capital D because the axis of bending is Y and the dimension perpendicular to it is capital D, and this 450 is your B. I hope you understood this. Okay, now to select the chart, what else we need? The first thing that we need is D dash, that is the effective cover. So that will be the first thing that I will be finding. So as per clause 26.4.2.1, clear cover is 40 mm, assuming link diameter to be 8 mm and assuming longitudinal reinforcement to be 25 mm, then the effective cover comes out to be 40 plus 8 plus 25 by 2, which is 60.5, right? So if this is the longitudinal reinforcement and this is the link, then this would be D dash, correct? And the ratio that we are interested is in D dash upon capital D. So I told you that what is the capital D here? This is the capital D and this is B, right? And by the way, if we are considering XX to be our axis of bending, what will be capital D and what will be B? If XX is the axis of bending, capital D will be this one perpendicular to it and B will be this one that is parallel to it. Fine. And if you get confused, you can always refer to SP16 because SP16 has to be allowed in the exam. Now D dash by capital D is 60.5 divided by 300, which is equal to 0.2. So we need to select the chart which is having FE415 and which is having D dash by capital D as 0.2. So for that we will first find PU by FCK BD because these two ratios are required, PU by FCK BD and MU by FCK BD square. PU is 1400 into 10 raised to 3 divided by FCK 25, B is 450, D is 300, so it comes out to be 0.4148. Second, MU by FCK BD square, so 90 into 10 raised to 6, this is MU, divided by FCK B D square, which is 0.0889. So these two values I got. Now this is that chart FY415 and D dash by capital D is 0.2. So let me see which is that chart number. It is chart number 34. Okay, chart number 34 of SP16. Yeah. So PU is 0.4148. You have to plot this. So see, this is your MU by FCK BD square and this is your PU by FCK BD, and it somewhere intersects in between 0.06 and 0.08. So let me take rho by FCK, this ratio of rho by FCK to be 0.07. So rho will come to be 0.07 multiplied by 25, which is 1.75%. This is the actual steel reinforcement that we have to provide, 1.75%. And if you remember, the first step itself, the first step that we did was to assume the steel percentage, and we assumed it to be 2%. That was an assumption, and that led us to getting the actual reinforcement percentage, which is 1.75%. So this is what we will be using. So rho is 1.75% is equal to 100 AST upon BD. You can see here that they have also given this formula, that AS is rho BD upon 100. So everything they have given in this chart itself. We need to find AST now. AST comes out to be 2362.5 mm square. Okay, so we need to estimate longitudinal reinforcement. Providing 8 20 mm dia for this 2362.5 mm square. You have to calculate the number of bars and dia combination by yourself, because we have already done this a lot of times, and I am getting 820 to be optimum. Now this 820 I will be placing in which direction? See, if this is the axis of bending, which is YY for us, the reinforcement have to be placed here along B. So I will have to place this 8 reinforcement like this: 1 2 3 4 5 6 7 8. Okay, so like this I'll be placing them. Now let us check all the horizontal spacing and all. Horizontal spacing means here like this spacing, and that whether we should provide an extra longitudinal reinforcement here or not, that we just have to check, because here it is given that spacing of longitudinal bars measured along periphery of the column shall not exceed 300 mm. So here definitely it will not exceed 300, because 300 minus 2 into 60.5, this is the D dash, let us say, which is 60.5. This will give me 179 mm of spacing in between, so it is definitely less than 300. Therefore we do not have to provide any other reinforcement in between. This is just a check, a normal check that you have to do. Then we need to calculate the minimum steel, which is 0.8% of cross sectional area, which comes out to be 1080 square mm. Then maximum steel 6% of cross sectional area, which is 8100 square mm. Minimum bar dia is 12, which we are already given 20 mm. So everything is fine according to this clause of longitudinal reinforcement. Step 5 is to estimate the transverse reinforcement. So this step remains the same as what we had done previously. The diameter has to be taken from the clause 26.5.3.2, which says that the link dia should be greater than 5 main by 4, which is 20 by 4, which is equal to 5 mm. So it has to be greater than this, and minimum dia has to be 8 mm. So I will give 8 mm dia, and the spacing will be from a criteria of these three, which is 300 mm, that is the least lateral dimension of member, 16 times the smallest dia of longitudinal reinforcement, which is 20, and third 300. Then the spacing is minimum of these three, so I will take 300. Therefore providing 8 mm diameter link at 300 mm center to center. Okay, so now we have done everything. We have done with the longitudinal bars, and we have also done with the transverse reinforcement. We just have to now show the detailing. So this is how the column is going to look. There will be a 8 mm dia at 300 mm center to center of link outside, correct? And these bars are 8 20 mm dia bars. So that's it. This is all that you have to do in columns for uniaxial bending. In the next lecture we will be solving a numerical with column having a biaxial bending, that it is bending about both the axes. So till then, take care. Thank you.